So just the next step in our discussion about languages is, maybe it would be good just to kind of review what we went over last time. If we had a language, and for languages like a bunch of A's and then a bunch of B's, and we said I and J are integers that are greater than 0. So we're starting to, one thing I hope we're getting is that languages and sets are technically the same thing, right? A set is a bunch of collections of letters. And then if we say, well, some of them are part of our language and some of them are not, then that, it's kind of like saying they're in the set or they're not in the set. So if we said all the words, let's say our alphabet is just the letters A and B. So we have a 2-letter alphabet, and we're saying that we have a particular language or a particular set. It's really the same thing. If we said that we only want words that start off with a bunch of A's, and then after seeing the A's, then we start seeing maybe a bunch of B's, and then those are the only ones acceptable. So for example, A, B is in our language. We see some A's, there's at least one, because they have to be greater than 0. There has to be at least one A. After we see A's, then we're going to see at least one B, but maybe many more. So this would be considered in our language. So we have to come up with some kind of a machine that will read this and answer yes. Now, is this in our language?
No.
No. And what's the problem? The problem is, what is it?
Because like in our language we have like A's followed by B. That's it.
Right, and once we see a B, we should never see another A.
Yeah.
Okay. Would this be in our language? 2 A's?
No.
No, because J must be greater than 0. We must see at least one B. All right. So if what about this? B, A, B, B.
Yeah. No, I guess like the order is not fine. So like we need to have A, then followed by
right.
B.
The very first thing must be an A, at least one A, maybe more. Then once we switch over to B's, we can only see B's. So we have to come up with a way to, we have to come up with some kind of a computer program. We'd like it to be as simple as possible that can answer yes or no to these. So we come up with a finite automata. We'd say we start here. This is like at the beginning of the string. We read an A, and we go to a state, and this state basically means we've read at least one A. So if we start off here, if we ever get to here, that means we've read at least one A. Now we might read more A's. So if we read more A's, we just stay here. We're in the phase where we're reading A's. Eventually we go to read a B, and we're now moving into a state where we can no longer read A's. And once we're in the state where, once we get to this state, this means we've read at least one A, maybe more, and we've read at least one B. Now if we read more B's, that's okay. More B's are fine. Now, we're going to put a double circle around this one. Some textbooks use double circles to mean this is we answer yes. Other textbooks type the words yes and no in the state. Meaning, if you read a bunch of letters and you're in this state, when you run out of letters, the answer is no, it's not part of our language. So if we read 1A or 2 A's or 3 A's, and then the word stop, the answer is no, because we don't have a B. Once we get to the point where we read a B, we're in a yes state. We could read more B's and it stays fine. If the first thing we read is a B, that's no good. And we're going to create this state. This is called a trap state. This is a state, if you ever get here, you're dead. You'll never come out. So you could read all the A's and B's you want. You're going to stay in this state, and it's going to always answer no. So this is sometimes referred to as a trap state. So when we're in this state, we read, and the only letters in our alphabet are A and B, so we can only read an A or a B and we have to go somewhere. In this state, you read an A, you stay here, you read a B, you jump here. In this state, you could read B's and stay, but if you're ever in this state and you read an A, then we have a problem. You go into the state where you're going to fail. This would be if you read an A. So, this is the finite automata for this language. You can take any word you want, start here, and just as you read the letters, hop around from state to state. At the end of the letters, if you're here, it's in our language. And if you're not here, if you're going to be somewhere, if you're in one of these three, you're not in our language. So, what did we say was no good? A, B, B, A, we said was no good. What would happen? Well, we would start here. We read an A, we read another A, we read a B, we read another B, and then we read an A, and we're stuck here. The word ends and we're in a state that answers no. So this is not part of our language. So this is the equipment you would need for this particular language. So now I think last class we left off saying that what if we had the rule that it's a bunch of A's, our language is a series of A's followed by a series of B's, but now we have a new restriction. The number of A's and the number of B's have to match. Does this make the problem harder? Well, does it seem like it makes it harder?
A little bit, like it's easy.
What's that? Just off the top of your head, does it make it? So really where we're going with this, where we're classifying languages as, you know, it's in this group, or it's in this group, or it's in this group, it's how difficult it is to build the equipment that's going to answer yes or no, is it in the language? So the question now is, does this new rule, saying the number of A's and the number of B's must equal, does it make it harder to answer yes or no? Can we still do it with a finite automata? So can we say, let's say we'll start at a state, right? We have to read, I just has to be greater than 0. So we have to read at least one A. So we read an A. So starting here, we haven't read anything. Once we get to here, we've read an A. If we read an A, what do we have to do? We have to read exactly one B. We can't read 4 B's, that's no good. So we have to, somehow we're keeping track of how many A's we've had. So I'm going to start going downward. If I read a B, then that's good. And I'll put a double circle around here and I'll write yes in the box. If we read 2 A's, then, so if we start here and we make it to here, that means we've read exactly 2 A's. Now if we read exactly 2 A's, then we have to read exactly 2 B's. So we'll read a B. So if we get to this state, that means we've read 2 A's and 1 B. Now we have to go to another state, and this is acceptable.
Yeah.
Now we're going to keep going. This is going to go forever. So the reason this is a more difficult computation, our computation means you give me a bunch of A's and B's and I'm going to answer yes or no. That's the computation we're doing. The new restriction is I have to kind of keep track of how many A's I read and then kind of count, you know, subtract them. Somehow keep track of how many I've read and how many B's I've read. So if I get to this state, I've read 2 A's and 1 B, and then I could have a state where, you know, I've read 6 A's and 3 B's, but only the ones where the number of A's and B's match are acceptable. So how many states would this machine have to be if we keep going? Would it be a finite set of states? Or would we have to just keep building this thing infinitely? We don't know the input number, how many A's and B's. It could be a very large, no, it could be 10 billion A's followed by 10 billion B's. So we have to make this thing like infinitely long. So what we talked about last class was if there's a finite number of states, if we say, oh, I'm going to build a machine that has, you know, it could be a large number, it could be 10 billion, but it's a fixed number, it doesn't change, and we can handle any input. It looks like with this new restriction, A's and the B's, it almost seems like the same language, it just has one more restriction. The number of A's and B's have to match. Makes the problem a lot harder. So, can you think of now, as a computer programmer, can you think of a way to solve this? We're going to, if you wrote a program in Java or Pascal, C++, you would probably create a variable that has a state, like I'm reading A's right now. Maybe you can call the variable state, and you'd set it equal to A's. Now you're reading A's, you're counting up how many A's there are. Then once you read your first B, you would change the state to say reading B's, and then start counting up B's. So you might do it something like what we had before. You might do something like this. I'm going to read an A, and then I'm going to read more A's. Read as many A's as I want. Then I'm going to read B's, and then I'm going to read as many B's as I want. But there's a new computation we have to do, and what's that computation? We need to count up how many we've read. So when we're going to read an A, we're going to also do, when we read an A, we're going to add a 1 to our counter. So we're going to start off with the count equals 0. So this is really our start arrow. I'm going to put it here. Count equals 0. So before we even start reading the letters, we're going to start some counter off. So we now have a counter. And we're going to start it off with 0 in it. So we now have, in order to solve this, to build a machine that can answer yes or no, what's in this language, we're going to create a finite automata, and we're going to have one variable just to keep count, right? So this should work, right? So what we're going to do is we read an A, and then we add a 1 to here. So let's say our input value is A, B, B, B. Let's say that's our input. Now, is this string in our language? Is this in this set or in our language? And the answer is yes, because the number of A's matches the number of B's. So here's how our machine is going to detect that. It's going to read an A and change this value to a 1. And it's going to jump to this state. So now we're in this state. We read another A. We stay in this state, but we're now going to add another 1. So every time we see an A, we add 1. When we see a B, we're going to subtract 1. And if we see another B, we subtract 1 again. Okay, so we read the first A and we're in this state. Now we read the second A. We add 1. We stay in the same state, but we add 1. We read the third one. We stay in the same state, but we add 1. So we're now saying we're in the state where we're reading A's, and we've recorded that we've read 3 of them. Now we see our first B. So we jump over to this state. This is the state meaning we're now reading B's, and we subtract 1. This becomes a 2. Then we read another B. We stay in this state and we subtract 1. Now there's a 1. Yeah, well, so let me first do this. I'm going to say I'll say without this B and with this B. We'll compare the two. So suppose we're in this state. We've read these 5 letters. We are now in this state. I'm going to put a double circle around it, and I'm going to put a yes in the box. But we're in this state, and our counter says 1. Is this word part of our language? And okay, it's not. And why is it not part of our language?
Because the counter value is not set to 0.
Counter, right. So the new rule is this. When we read a word, we have to not only end up in the yes state, but our storage, the new thing is we now have storage. We're going to make rules about the storage. And in this case, the storage has to be equal to 0. So if there was a B here, then we would read the last B, and this would become a 0, and then we can answer yes. So a yes is now, not only do we have to be in yes state, but our storage has to meet some condition. Okay, so this language, because the number of A's and number of B's have to match, is considered more difficult to compute. The reason, and we were required to add this piece of memory. What if we had a language like this? So now, here's what I'm going to start to get at. I'm going to start to get at some computations are going to require even more memory. And we're going to try to decide, based on how much more memory it needs, we're going to say those problems are more difficult ones than ones that need a little amount of memory. So we're going to try to put computations into classes of how difficult they are. But suppose we had a language that was like this. I'm going to change the alphabet. I'm going to add 2 more letters, C and D. And I'm going to say the language has a number of A's, then a different number of B's, then the number of C's has to match the number of A's, and then the number of D's has to match the number of B's. And I'm going to say I and J are greater than 0. Okay. How would we solve this one?
The 2 counters.
2 counters, right? Is there any way to do it with 1 counter? I've thought about this. I can't see any way to do it with 1 counter. We could have done it with 1 counter if the A's and the B's had to match, because we can count up the A's and count down the B's, and then the counter is 0, we can start over. But because we're going to read some A's, we have to remember how many we've read. Then we're going to read some B's, and that's a different number. Then we have to go back and make sure this matches that. This is going to need 2 counters. So we can start making the argument, maybe this problem is a little harder than the previous one because we need 2 counters instead of 1 counter. So the languages that require not only a finite state machine, something bouncing around from states to states, but also need some memory, we're going to try to characterize them in the simplest way. We're going to try to say we need a state machine and memory, but we don't want you, as you hop from state to state, we don't want you to spend an hour playing around with the memory, right? So here's what we're going to do. We're going to try to say the languages that need 1 memory cell and 2 memory cells are going to be put into the same class. But we're going to say you're allowed to use a certain amount of memory, but when you go to the memory, you're only allowed to, let's say for example, we had, our computation requires 4 memory cells. Right? Now you're saying this one would only require 2. Let's say we had some other language that requires 4. Okay. Every time, so we're bouncing around from state to state. We have a state machine that makes us bounce around. We're bouncing around from state to state, and maybe a couple of the states are yes states, a couple of them are no. But we're also going to have a rule that the memory must, maybe it all has to equal 0 or something, some rule about the memory. As we go from one state to another state, we're going to allow you to add memory as needed. But every time you go out to your memory, you're only allowed to perform 1 operation. Right? So for example, let's say you have 4 memory cells, and this one is equal to 2, and this one is equal to 6, and this is 9, and this is -1. We're going to have a restriction that says, so we're not going to restrict it that says you only allowed 1 memory cell, and then the next class of problems are the ones where you're allowed 2, and so on. So, you have a question?
Yeah, do we have a negative value?
Maybe.
It's like I and J are like greater than 0.
Well, no, in this case, it would never go negative. Actually, maybe you want it to go negative because maybe there's more C's than A's, and if this came out negative.
Okay, the counter value it has to be.
Right, it's a counter value for now. But basically, what we're going to try to do is we're going to, as far as what's going to be called context-free languages, we're going to allow for your computation. We're going to allow you to have a finite state machine, a limited amount of storage, but we're going to put a restriction on the storage. And next class, we're going to talk about if we remove that restriction. So the restriction right now is, out of your storage, you can only access 1 of the cells per transition. So maybe you can add a number to it or subtract a number to it. And one of the things you can do is you can request another cell if you needed it. So you might say, oh, I need another cell You know, maybe as your computation's going, you realize maybe if there were more E's and F's and you needed another cell, oh, I need another cell. So as you're performing your computation, you're allowed to ask for more memory, but that's the only thing you're allowed to do. You say, I need one more memory, and maybe you store a value there, and then that's it, you're done. If you jump to another state, maybe that's a state where you don't get more memory, but maybe you look at what's on, you look at one memory cell, and then you can say, okay, I don't need that one anymore. But what you're not allowed to do for today's class, but what you will be allowed to do next class, you're not allowed to go reading all through the memory and go, oh, if I take 9 minus 6 and store that result over here, you can't perform some big computation. For today's class, you can only look at one of your many memory cells. So the question is, which one would we allow you to use? Let's say you started with one memory cell, and then later on said, oh, as I'm reading through the letters, I need a second memory cell. Would we allow you to use the first one or the newest one? If we allow you to use the first one, you're kind of hopping around through your data. So the idea was, and the reason I'm explaining this is it's kind of, it sounds kind of arbitrary where they came up with this. But we're going to allow you to have multiple memory cells, but at each transition you can only operate on one. And the reason we want to do that is we want to be able to say however many states you hop to, that's how many times you looked at a memory cell. So if you're only allowed to look at one, then we can kind of count how many memory operations you did. If you're allowed to look at all the memory and sort the memory and all that at all different stages, it becomes more difficult to count it. So we want to allow you to have multiple memories, but we only want you to operate on one cell at a time. Well, if you're going to build the cells as time goes on, it's kind of like you're stacking up the cells. You're starting off with one cell and then you're saying, oh, I need another one. So you add another one. So you're writing numbers in here like 2, 8. And if you go to access it, you should access the most recent one and then decide to get rid of it or not. If you start getting rid of it from the bottom, then it's kind of like you're reading through your memory. So it's almost like you're cheating. So what we're going to do is we're going to say that you can, we're going to say this, we're going to say you can have a finite automata for this. You start off at A, you read in A, you perform a memory operation. As long as you keep reading A's, you keep performing a memory operation. Then you eventually read a B, you can read more B's, and this is a final state. But the only operations you could do as far as memory is concerned, the only operations you're allowed to do are ones where you can add memory or delete memory or look at what the most recent value of your memory is. So we're going to have a stack, which maybe will start off as empty. And you're allowed to, at each step, you can request a memory location and store a value in it, or you can look at the memory location at the top and delete it if you want. But that's it. You can't do anything else. So you have more than one memory cell, but there's a restriction on how much activity you could do with each hop. And we want to limit that so we can say this is a class of easier problems. And like I say, next week we're going to say on one hop you get to read up and down the whole thing and change it all around per hop. Those are obviously going to be more complicated languages. So now what we can do with this new rule, we have memory, we can expand it as needed, but at each action we're only allowed to put something on the stack or pop something off the stack. So we read an A. We're not going to use a counter now, we're just going to start storing A's. So we read an A and we store an A. We read another A, we store another A. We read another A, we store another A. Now we read a B, so we're going to pop. Pop off. Have you taken data structures?
Yeah.
So have they covered stacks?
Yeah.
Okay. So now when we see an A, we're going to say push an A. If we see an A, we push an A. If we see a B, we pop an A. And if we see a, if we see a B, we pop an A. So now, after seeing three A's, let's say our word is A, B, B, like last time. We push an A, we push an A, we push an A. Now we see a B. What are we allowed to do? Well, we have three memory locations, but we have this restriction that you can only access one per letter. So, then the only thing we can do, if we let you randomly pick one, then the access time to it's going to take time. So the only one we're going to let you see is the top one. If we let you see anything else, then you'd be pushing stuff on the top while looking at the middle, and then it's open for you to be cheating. Okay, so you pop this one, and you read this B. And then you read another B, and you pop this one. Now, is this a letter in our language? And the answer will be no, even though we're in a yes state, even though we're in a state that says yes. Because our rule about our memory is the memory should be clear. So it used to be we were counting them up and then we wanted it to be 0. Now we're pushing letters on, kind of as a counter. And then our rule is we have to be in a yes state plus we have to have an empty stack. So if there was a third B, we could answer yes. So what a stack is, it's a block of memory, but it's very restrictive on how we could use it. It's not like what we do when we write computer code. We can access the all our memory, all our variables that we choose. So it's memory, but it's very restricted in how we could use it. So the set of languages, let me erase this. The set of languages that can be detected by the set of languages that can be detected by a finite automata, so that's a collection of finite number of states, some labeled yes, some labeled no, with the addition of a restricted piece of memory, a stack. If you can answer yes or no using a finite automata plus a stack, which we're going to call these two put together, we're going to call this a push-down automata, which implies it's an automata, meaning you automatically hop from state to state, and then the push-down part is you're pushing stuff onto the stack. But it should be called like a push-pop memory automata, might have been a better name for this. So we're going to say all languages, we're going to call these context-free, and in a class or two, we're going to look at other types of languages, and then we'll see there are languages where the context, where the letters appear, are required to be based on where other things appear, and that's going to be sensitive to where the context is. But right now, this name might not make sense, but we're going to call these context-free languages. Context-free languages, we can build a machine that answers yes or no by using a finite automata with the use of stack memory, which is really restricted memory. Okay, so now what's going to come up as we go into different languages, different classes of languages, we're going to find that the more equipment we add, and the more equipment, so that's memory, the more equipment we add, we're going to call that space, and the more time we allow means the computation is harder to do. So we spoke last class about regular sets or languages, and like I say, we now realize sets and languages are the same thing. We had regular languages, which are the languages that can be detected by a deterministic finite automata with no stack, no memory. Now we have a new class called context-free languages. Those have a deterministic finite automata plus, in addition to that, a stack. Now, if you remember from set theory, if we were to draw that set, how would we draw it? Is it a separate class? Are these the context-free languages?
No.
Is one a subset of the other?
Yeah, regular one would be the subset of context free.
In its entirety? Or could it be like this?
No, entirely.
Could it be like this?
No.
Like some regulars are not context-free? Okay, and what's your argument?
Regular one plus stack gives you context free.
Right, so if
every
we could,
every regular thing will be a subset of context.
right, because it just means you had the choice to use a stack and you chose not to.
Yeah.
Right, so the ones that are out here, so we could have context-free languages. The ones that are out here that are not in here were the ones that actually required the stack
Yeah.
to be used. The ones that don't require a stack, they're regular and also context-free. Right, so yeah, so what we want to do is, we're going to cover, so where we're really going with this in the theory of computation is, we want to create classes of problems. We want to create classes of problems, and we want to say this class is harder than this class is harder than this class. And to a computer scientist, these two classes probably don't come up too often in computer science. It's the bigger classes that are going to matter. But we're going to later on be able to answer questions like, if you work at Facebook and they have 9 million users, and you type in your password, do we want to do a linear search through 9 million users looking for your password, or do we want to try to find it? Do we want that computation to be done faster than it already is done? So that's going to be a computation that's out here somewhere, and we want to push it as close to, let's say this is going to be an expanding, the center is like the easiest computation in the world, and our goal is to kind of figure out where we are and push it closer. So, of all the different types of languages, there are also corresponding grammars to them. So, let me go over an example of what a grammar is, since we have a few minutes left. For example, in the English language, and I guess any language, a grammar would look something like this. You have a sentence which is made up of a a sentence is made up of what was a sentence made up of again?
Words, list of words.
Right, but what I'm going to do, I'm going to use a restricted version of English. I'm going to say it's made up of a subject followed by, I'll put these symbols just to let know it's something, followed by a, what do you call it, a predicate? Right? Okay. So now the question is, so in other words, like, I'm going to say, for sentences, I'm going to say, like, you have to say a noun, like, the dog barked. So like, yeah, a subject and then what it did. So a subject is now, a subject is made up of, a subject can be a noun, and it could also be a collection of adjectives. So it could be an adjective followed by a subject, or it can be just a noun. Okay, and a predicate, and I don't want to make this too complicated. A predicate can be made up of adjectives, adverbs, followed by a verb. Followed by a predicate. Or it could be a verb. Now let me just explain. So what we're doing is we're writing a set of rules to follow, and then we're going to ask ourselves, is something a sentence in the English language or not? So suppose I said, the dog read. I don't know if it's brown. There's no red dog, it's brown. Is this a sentence in the English language? Well, these are going to be the rules that tell us yes or no, is it a sentence? So we're going to say, okay, sentences start off with a subject followed by what the subject did, a predicate. So we could say the dog ends up being the subject, this could be the subject. And then this part would have to then be the predicate, but it's not. It's, all this is an adjective, something to describe the dog. So this would end up being not a sentence. But if we said maybe like the big brown dog the way I wrote this, all the adverbs have to be before the verb. So I'm going to say loudly barked. This would actually be considered a legitimate sentence the way I wrote out the grammar. So again, this is kind of a different topic, but what I'm getting at is there is a corresponding grammar to every language. And so then there's going to be regular grammars and context-free grammars, and then in other classes we'll have other types of grammars. So in this case, we have the dog is the noun. So this is like, I think I remember learning this like in second grade, and I couldn't understand any of it. But, and then this is a list. This is an adjective, and this is an adjective. And technically, I forget why, but this is also an adjective. Again, this is not an English lesson tonight, so, but the means you're talking about a specific dog, so anything that helps describe the noun is considered an adjective. So the way we've written this is we can have as many adjectives as we want. We can have 0, but we can have 1 or 2 or 3. Actually, we can have as many as we want, because we said a subject is an adjective followed by a subject. So it just keeps like recursively defining itself, and then eventually there's a noun too. And then the same thing is true for, right, this is an adverb, and this is a verb. And we require, based on our language, we require every sentence must have a subject and must have a predicate. And then we say for each of these, we describe what those break down into. And as long as our sentence has this, it counts. So now this is a really bad version of English. What actually is acceptable is, well, this would be a sentence, dog loudly barked. Because there's a minimum of a noun. A noun is required. Adjectives get recursively defined. We could add 0 to as many as we want. And this could also be gone. Dog barked, according to this grammar, is a legitimate sentence. Dog by itself is not, because we're missing a predicate. So, I don't know if you remember anything like this when you were like in second grade for language. Okay, and every language has a different grammar to it. So, considering computer languages are the same thing, we might define, like let's say we have, in computer languages, we might have an expression like this, A equals B, semicolon. You say, okay, yeah, that's part of Java, C++. We could say A equals B plus C, semicolon. Yeah, that's allowed. We could say A equals open paren B plus C times D, semicolon. That's allowed, right? And an example of something that's not allowed would be like A equals close paren B D semicolon. That would say, wait, that's no good. The compiler would say no good. So we're going to, when we do our language, we're going to need to write out a grammar for it. So the grammar for our language might look something like this. So this is going to be kind of the same thing we just did with English. We're going to say, textbooks usually use as, some tech authors say it means start, and some say it means sentence, like it's coming from natural languages. But our start symbol, or these are, let's say, sentences in our language. A sentence is made up of an identifier, followed by an equal sign, followed by, now what comes after this? Now let's say this is a very limited version of let's say Java. All we're going to do no input, no output. All we can do is like sentences like this stuff equals that. And it always gets written over to the left side. So we could have an identifier. What comes after the equal sign could be an identifier. It could be an operation like an identifier plus another identifier. Or it could be like an open paren. It could be like a big collection of stuff. So we're going to define it this way. We're going to say it's an expression. And we'll define expression later. And then it ends with a semicolon. So we're saying all sentences in our language are of the form an identifier, an equal sign, some kind of an expression, and then we always end with a semicolon. Right? Like in the English language, and sentences end with a period or a question mark. In computer languages, they usually end with a semicolon. All right, so we'll define our identifiers are equal to like A or B or C or D. Let's say there's only 4 variables our language is allowed. Okay, equal sign is an equal sign. It doesn't become something else. So now what we have to do is we have to define an expression. So an expression can be what? It can be an identifier by itself. So it can be an identifier. Or it can be an identifier followed by an operator followed by an identifier. It could also be this whole thing followed by an operator, this whole thing. So this, we're going to say in a vague way, this is an expression times an expression. This is really an expression plus an expression. So we're going to say it can be an expression followed by an operator followed by an expression. And we're also allowed to do open parens and closed parens. So we're going to say it could be an expression inside parentheses. So the first time seeing this, if you took a compiler's class, you're going to do this. Half the course is just, half of your design is going to be this. And then I'm going to define operators like this. Operators are like plus or minus or times or divide. It says 4 operators. So what we've effectively done here is we've written a grammar that describes all of these kinds of sentences. So now the question is, if we were to write code that's going to read this and answer, yes, that's a legitimate sentence. Yes, that's a legitimate sentence. Yes, that's a legitimate sentence. And read this and go, no, that's no good. So we're now like almost talking about like compiler design. How would we do this? What we would do is we would create a finite state machine with a stack. And our stack would go like this. We would put on our stack, as we read stuff, we're basically reading, let's follow this line. We're reading an A, so we say in A, we expect to see an identifier. The only thing we accept is something that eventually equals the state of the S. We read an identifier, so we've read an A, and we have an identifier. We're just recording stuff on our stack. We then see an equal sign. So we've read an A, we've read an equal sign. Now we see an open paren. We ask ourselves, what could an open paren be? Well, we'll put an open paren here, but it looks like it better be an expression, and the only expressions are the identifier type, the expression, the operator expression, and the open paren followed by an expression followed by a closed paren. So it looks like this is the only thing we could possibly see. So we haven't read the closed paren, so we don't know if it's going to come out screwed up or correct. So we read the next thing, a B. That's an identifier. So we read identifier. We see a plus sign. That's an operator. And this is, I'm just showing you like kind of the computation that a compiler does. But it's following a context-free grammar, and it's using the push-down automata. So we have an identifier, followed by an operation, followed by an identifier. Now you're at the top of the stack. You're in a position to say an identifier after an operation, which is after another identifier. This is an expression. So really B plus C is an expression. So we can pop this off. And we can go pop, 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 and just say this is an expression. So what we've done is we've read up to here. We've read up to this point. And based on our grammar, we have seen an identifier, an equal sign, an open paren, and what we now consider an expression. So we're keeping on top of the stack everything we see following the rules of our language, following the grammar. Then we see a closed paren. So we read here, and we put a closed paren up here, and we say, an open paren followed by an expression followed by a closed paren, that's an expression. That's this rule. This is another way of saying that's an expression. So now, this collapses, and we have, do this. We're here. So far, we've read up from A up to here, and what we've read is an identifier, an equal sign, and a fully qualified expression. Now we see a star. We don't know what that is, so we're hoping we just record it here, because a star and an E means nothing to our language. Then we read another identifier. So now we're up to here. We've read this thing. And we find that, oh, I'm sorry, this is an expression. The D can be considered,
Identify.
yeah, I'd have to, oh, right, okay. So, yeah, this can be an identifier. I have to, maybe I should have defined this a little bit different. I would have to add a rule that says identifiers operate on an expression is also considered an expression.
Yeah.
Yeah, okay, so I would need that rule too. So now an identifier, a multiply sign, and an expression, this can collapse into an expression. So now that we've read from A all the way up to here, we've actually seen an identifier, an equal sign, and now this whole thing is considered an expression. And then we read the semicolon, and now we have a rule that says an identifier, an equal sign, an expression, and a semicolon. This collapses and becomes a sentence, or the start symbol. And the idea is we would build a finite automata that reads through any expression, adds and subtracts stuff from the stack, and if the stack hits the final state where there's just an S here, then we accept. Otherwise, it's no good. Everything else would kick out a compiler error. So that's really like, so that'll show up in parts of computer science, parsing strings, and actually you say you took a database class. Did you do a parser?
Yeah.
So you must have stored stuff on a stack. Had to be, yeah. So it's the only way to do this computation. So